Okay, so the topic of today's lecture is an introduction to the matting problem and a discussion of number one, how does blue screen matting work? You know, kind of the basic blue screen, green screen stuff that you see in DVD special effects videos. And then talking about introduction to the problem where we don't have a bright blue or bright green background, right? And that's a topic that has been studied a lot in the computer vision and computer graphics communities and is only starting to make some inroads into how people do it in, in the visual effects industry. So first, I guess let me talk about, what is the matting problem? So the matting problem is basically like this. So you have a composite image on the left-hand side. In some sense, what we want to do is we want to take that image apart into pieces, right? We want to say, okay, the foreground is this guy by himself, and the background is just the tree, and the mat is basically here it looks like a black and white image, but as we're going to see, typically this is more like a grayscale image that has lots of shades of gray around the edges of the objects. So here, this is basically like saying, everywhere the mat is 1, I'm taking pixels from the foreground. Everywhere the mat is 0, I'm taking pixels from the background. And in places in between, I'm mixing the pixels between the foreground and the background. So let me be a little bit more specific about how that works. So this is basically intro to matting. So in addition to the video, I'm also going to scan in these slides as a PDF and put them on the Piazza page too. So basically what we're saying is that we have an image, right? And an image is made up of pixels x, y. Okay? And actually, the way I think about this is actually a vector of red, green, blue, right? And so if you take an image out of your Photoshop or whatever other, image editing program you use, as you run your mouse over the image, you're going to see, lots of red, green, blue values, most of which range between, usually range between 0 and 255. That's the way that they scale it for typical digital images. In this section, I'm going to kind of switch back and forth between sometimes using 0 to 255 and sometimes using a normalized scale of 0 to 1. Okay, but the point is that every pixel is like a 3 vector. Okay, and what we're saying is that at a given location, what I have is some mixture of a foreground image and a background image. Okay, I just need another parentheses here. So what happens when alpha is 1? What I get is, that the pixel value is just the foreground. When alpha equals 0, I just get that then this zeroes out this and this term becomes 1. And when alpha is like 1/2, that means that I have kind of a halfway mixture. I guess I should say 1/2 f of xy plus 1/2 b of xy. Right? So most of the time we deal with images where, yes, many pixels are close to 0 or 1, and some pixels are kind of a fractional distance between the foreground and the background. Okay? And a lot of times, just because it's kind of clumsy to keep on writing this of xy, this parentheses xy, I'm going to usually abbreviate this equation to something like just the image equals alpha times the foreground plus 1 minus alpha times the background, with the understanding that everything here depends on the pixel value I'm at in the image. Okay? And so this alpha is, what we call the mat. Okay? And so the way I think about this is that, I, the original image, is a full RGB image. F and B are also full RGB images, and alpha is like this kind of grayscale image. Okay? Just tells me between 0 and 1, how do I mix those two things together? And so those of you that have taken some computer graphics are probably used to seeing this alpha in the context of the alpha channel, right, which is basically used when you're putting layers of material on top of each other. We're going to talk about that when we talk about the second chapter, or I guess it's chapter 3 of the book, which says, okay, once we've got these pieces of the image, how do we put them back together? So right now what we're doing is we're kind of taking apart an original image into these three pieces, okay? And so the first question is, you would think that, okay, well, I could take a picture of this room and I could draw a line around all you guys, and then I could basically just clip out each of you, and I could decide, okay, well, this guy has got 1 in the middle and 0 behind. Why aren't alpha values just always binary? And so one big reason for that is that, I should take my pen out of the picture here. One big reason for that is that, first of all, every pixel, right? So if I think about how a camera acquires an image, right? So here's my camera, and here's my image, and here's the world, right? So, this is, say, like the top view of a person, and this is the background with like a tree or something like that. So this is like top view. Right? So every pixel of this image is just kind of like this little quantized chunk of area, right? And so what's happening is, maybe I should have drawn it a little more like this. So here, this pixel here has got an integration of light that is coming in from basically everything that's inside this cone, right? So in this case, I'm getting some of the person in the foreground, some of the tree in the background. Just the fact that the pixels are, finite area means that there's always some mixing between stuff at different distances, okay? And you might say, okay, well, what about, super high resolution cameras, right? What if I had a 5,000 by, 3,000 image? Well, even then, like if you zoom in and we're talking about someone's like wispy hair or something like that, then even then, hair is really thin, right? No camera is going to have pixel value that is the width of a human hair viewed in the image, right? And so even then, you're going to have some mixing. And then another big reason is motion blur, right? So when you take an image, not only are you integrating every pixel over a small region of space, you're also integrating the light that's coming into the camera over a small amount of time, right? And so that means that when you have your shutter speed that's say 1/200th of a second, if the action in the scene is moving slightly, then you're going to get some basically integral of all the stuff that was happening in the scene over that small amount of time, right? So, let me just summarize by saying, why fractional alphas? One big reason is finite pixel size. Another reason is basically, finite shutter speed. Things like motion blur. And then things like kind of wispiness or fuzziness or translucency of objects. Yes, right. So you could have all sorts of physical phenomena too that might contribute to it, right? So yeah. So as soon as you kind of get into looking at real pictures, you'll see that you can't basically take a picture apart into its kind of cookie cutter parts. And so actually, here's a image to illustrate that. So here is a picture of a wispy object, right? A little pussy willow, blossom that I took in my backyard. Okay. So now, if we want to take this and we want to put it on some other background, say we want to put it on this wood grain background. Well, the first thing I could try to do is I could try to just say, okay, I'm going to do the best I can with outlining this object, right? It's fuzzy, so I have to kind of make a choice about where do I draw the boundary. And when I put that, that turns into basically a very simplified alpha map, right? Binary. Either stuff that's inside the contour is 1 or the stuff that's outside the contour is 0, right? If I were to do that and put that back on, here's like basically just the part of the image that is, inside that contour. If I put that back on the background, it kind of looks crappy, right? Because I've definitely cropped out a lot of the wispiness, and also, more importantly, I can see this kind of green background that is showing through that, since it's a binary map, I can't really do anything about, right? So what we really want to do is something more like this. Oh, here's a zoom in of saying, you can definitely see here, there's like this kind of cruddy green area where this stuff was clearly part of the original image, and I don't want that, right? When I do this hard segmentation, I'm definitely not taking advantage of the knowledge that things see through other things. And so this would be the ideal thing that I want to do, is to basically make an alpha map where if I were to zoom in on this, you would see shades of gray. And we're going to talk more about alpha, I'm going to show you some more zoom-ins of alpha mats in a second, so we'll look at that in a minute. If I could do this, then the composite looks a lot better, right? So then, you could imagine that this is getting towards this wispy thing living in the same plate or the same scene as the second image. Okay, so that's kind of where we're going. That's what we want to be able to do. Okay, so questions or comments so far? Yep.
There's still a little bit of green in there, though. Do you go about how to get rid of that or matte that?
Right. So I'll talk a little bit about that. I mean, so this was an imperfect map, right? So it's true that if I wanted to do this for a visual effects production, I would have to go back in and figure out how to do a better map, right? And in theory, one thing I could try to do would be to refine the alpha values to get rid of those green spots. And another thing that I learned when I was talking to people in the visual effects industry was that, even though for most of this section I'm going to be talking about the ideal goal of taking an image and turning it into foreground, background, and alpha, in practice, it turns out that what you really want to do is pay attention to the image that you're going to put this alpha matte back onto, right? So, I mean, if I was putting this, for example, onto a greenish background, I wouldn't really care so much about whether there was green showing through in the original choice of alpha. Right. But in an image like this, I would say, okay, well, now I have to go back and do more work. And so one thing that a compositor told me is basically that you are never doing this kind of matting problem in isolation. You're always thinking about where is this thing going to go next, okay? And so I'll talk a little bit about that more later. And so we'll also talk about, if the mat is not good, how do I do things like refine the mat and make it better? So that's going to be talking about that later on. Okay. Okay, so what makes this problem difficult? Okay, so let's go back to I guess I jiggled my screen here. So let's go back to the matting equation. So why is matting difficult or hard? Right, so here's the equation again. I have the original image. I have alpha times the foreground plus 1 minus alpha times the background. Okay. Now, this here is a 3x1 vector. This here is just a scalar, 1 by 1. This here is a 3x1 vector. This here again is 1 by 1. And this here is 3 by 1. Right, so I have to think about what do I know and what do I not know. And so basically what I have are, for every color channel of the original image, I have this matting equation. So what I have are 3 equations in 7 unknowns. Right? That means, I have alpha, I have foreground red, foreground green, foreground blue, background red, background green, background blue. I don't know any of those things starting out, right? And the only thing I have at every pixel is the RGB of the image, right? So this immediately shows me that I don't have enough information to uniquely identify, the foreground, background, and alpha. And so that presents a problem. And so if I look, for example, at here's an example where I have a left-hand image, and I have a bunch of possibilities for what the right-hand image could be. Okay, and this is not even a color image. This is just a black and white image, but the problem is still there, right? So you might look at this and say, okay, the first row kind of tells me, well, I could say that the foreground, so I could just choose an alpha mat that is entirely 1 across the whole image, right? So that's like saying that everything that you saw was foreground and there was no background. So for example, in the case of that pussy willow, that would be like kind of saying, okay, imagine that there was a guy holding a picture of this pussy willow to the camera, and the flat plane was just the photograph, right? So I'd be like saying, okay, well, yes, there's really only one object, which is the photograph the guy is holding. I could consider that whole thing to be the foreground. That's kind of what the first row means. And then the background, image, since it's getting multiplied by 0 everywhere, could be arbitrary, right? Could be anything I wanted it to be. The middle image is kind of more like saying, well, actually, let's look at the bottom image. The bottom image is maybe closest to what a human would think about, right? It'd be like saying, okay, I imagine that the background is a pure white thing, and the foreground is this circle with a triangle, and what I'm doing is I'm cropping out the circle with the triangle, and I'm putting it on top of the background, right? You could argue that is kind of like a perceptually natural thing for a human to think, right? Or, I could also imagine that what I'm doing is I'm taking so the middle one is actually kind of a weird thing. That's kind of like saying, okay, the foreground image is pure white, and the matte is like a triangle, right? A gray triangle, so it's half gray. And the background image is the thing with the circle, and what I'm doing is I am, taking a triangular part of this, and I'm putting it on top of here at half resolution. And so I end up getting the same final output, but that's a kind of a weird way to think about undoing the image, right? And then the crazy thing is that, again, all these guys have a fair amount of what I would call spatial coherence, right? In the sense that they all look like still shapes. But in theory, what I could do is I could make a alpha foreground and background out of taking, random pixels from all three of these things and mixing them together. So basically the foreground and the background and the alphabet could just look like static snow from your TV screen, right? So, this is why there's this big ambiguity, right? That says, okay, well, I just don't have anywhere near enough information to be able to take apart an image into, the foreground, background, alpha. And so one of the homework problems is, for a given image, I guess I'm going to make it simpler, for a given pixel, show me that there are these ambiguities. Show me that it would be possible to do it with a bright red background or a bright green background or a bright blue background. And so the natural thing that we want to do going down the road is clearly, these are better looking mattes, even if we don't know which one is right, than mattes that look like total static, right? And so there's certainly this notion that we want to have nearby pixels in the matte have nearby alpha values, right? And similarly, we want the foreground and the background. We know that if I take a picture of a real image, that typically, things most of the time change very smoothly, right? If I look at a picture like this, I can say, okay, well, the table is mostly constant intensity. The carpet is not changing that much. There are changes at edges, right? So when there's an edge between a chair and a table, for example, there are possible big jumps between, like, the background colors. But those don't happen as often as the low-frequency stuff. And so a lot of the algorithms we're going to talk about coming up are exploiting the fact that we expect some sort of a coherence in all of these three things, okay? Okay, so how do we even get started with the matting problem? So one thing that is very common to do is to give the algorithm a little bit of guidance, right? And so here's an example of a fuzzy object, right? And so you're going to see, like in this kind of work, there's lots of stuffed animals and stuff like that because they're fuzzy, right? And so this is actually from a website, and I'm going to show you that in a second, called alphamatting.com. And basically that was a website created by a bunch of researchers to provide the community with a way to kind of benchmark proposed matting algorithms. So they have a whole bunch of fuzzy objects, and they have a whole bunch of ground truth mattes, meaning that they know exactly what the matte should be. And I'll talk about that a little bit later in this lecture, how do you obtain the actual matte. And then you submit your algorithm, you run it on these images, and then it gives you kind of a score about how well that you did, okay? And so one way that you can kind of help out a matting algorithm that we're going to talk about in a second is to provide it with what's called a trimap. Okay? A trimap is basically a binary image that the user draws that says, okay, I'm going to just label pixels as either black, white, or gray. Okay? White means that the pixel is definitely fully inside the object. I know that that pixel has alpha equals 1, right? So for an opaque object, that's just like, non-ambiguous. And then I have black pixels, which are like unambiguously the background. Okay, those pixels are for sure 0. And then I have this gray region, which is like the I don't know region. Okay, and so if you look back and forth between Eeyore and here, you can kind of see that there's lots of pixels that I could easily label as all foreground or all background, and then there are a bunch of pixels that are ambiguous. I don't know what those numbers are, and I have to figure them out, right? And so you can see that the gray regions are all in places where the fuzziness occurs, right? So in places that are kind of like around Eeyore's contour here, like this, the trimap is a little bit narrower, right? Because things are not as fuzzy there. But in places where he's got this kind of tail fuzz and head fuzz, the trimap is kind of a lot larger, just to convey that the human doesn't really know, how to draw that. And so for my pussy willow example, this is kind of a trimap that corresponds to that example that I used to build the map that I showed you earlier. So as we'll discuss, this Trymap is the input to some matting algorithms, okay? And it's not hard to do. You can just go into Photoshop and you just kind of color over, stuff that you know is in the middle, stuff that you know is in the background, and everything else gets turned gray. But that's a little bit laborious even still. As we're going to talk about, probably not so much today, but next time, is it's easier just to have a stroke-based algorithm, which means that you take the original image and you just draw on top of it and say, okay, all the white stuff is definitely foreground, all the black stuff is definitely background, you figure out the rest, right? So in some sense, this gives the matting algorithm a lot less information, but it's a lot easier for the human to do. Because doing a Trimap, with something that's really fuzzy could be like a laborious and painstaking process, whereas stroking on an image is just a really fast thing. You just do it in Photoshop, save the image, and then you're done. Okay. And so let me just show you alphamatting.com. So here, what you can see is that there are a whole bunch of data sets that correspond to, mostly fuzzy kinds of objects, dolls and troll dolls and elephants and stuff like that. And there's some really tough ones, right? So here, for example, are plastic bags and like mesh netting. Those are really hard for alpha matting because you can imagine that understanding what is supposed to happen in a region like a mesh bag, that's pretty tricky. And then along with those come Trymaps. And so if you scroll down, these are like various information. And then, let's see, where are the Trymaps? I guess the Trymaps are what I showed you earlier. And then if you look at the evaluation tab, you can see that people are submitting, these are all different algorithms that have been proposed in the literature, and these get ranked according to how well they do according to different metrics on these images. Okay. And so if any of you have seen, like, if you've heard any computer vision work on the stereo problem, which we're going to talk about in a couple months, there are similar algorithms like this for other computer vision problems, and these benchmarking data sets and web pages have turned out to be really useful for the community because it used to be that you would, go to your lab, you take some pictures, and then you would report some results, but you had no way to compare your algorithm to anyone else's. These kinds of websites provide a way for people to do that. And there's even some code available for matting. Not a lot, actually, compared to other research areas, but if you look at the code tab, you can see that there is a little bit of publicly available code, some of which I linked to on the first homework assignment. And I guess this is thinking about loading, so while it's doing that, let's go back to the lecture. Okay. All right, so what's next? So let's talk first about Bluescreen Matter, right? So that's the most familiar kind of matting, and that's the thing that still is used a lot in Hollywood today. And even though it's so pervasive, I'm not going to really say that much about it because it turns out that it's not that hard to talk about, right? That's why everyone does it, is because there are pretty good solutions for blue-screen matting, okay? And so kind of the history of that is that there were a couple guys, and I don't remember when it started, maybe the 40s or the 50s. The guy's name was Vlahos. And so he designed the first kind of blue-screen matting algorithm. And actually, even before that, they had designed some pretty slick algorithms that involved not blue screens, but like yellow light that was used as kind of a rear projection to make mats. And so basically, all the blue screen stuff that you see, someone, this guy Vlahos won a bunch of Academy Awards way back when for his original algorithms for blue screen matting. And so let me just say kind of the general idea. So the general idea of one of those algorithms, I mean, he has a whole bunch of patents and they kind of get refined over the years, but kind of one idea is that I take the alpha mat and I produce it as follows. Oh, I'm sorry. This should be a 1. So what does this mean? This is basically saying that I'm generating my alpha according to some combination of the blue channel and the green channel of the image. Okay? And so let's think about how this would work, right? So for a blue screen, right, I expect that a blue screen pixel that's really the background is going to have the blue channel basically very large and the green channel be very low, right? And so these A's are basically like kind of tunable parameters. So what I may do is I may have a couple knobs where I acquire my blue screen image, and I kind of turn these A1, A2 knobs until I'm happy with the map that I get. Okay, so I mean, this is fairly heuristic. I mean, from a computer vision perspective, there's not necessarily a lot of, you know, hardcore algorithmic mathematical reasoning for why this works, right? But it does work okay. And so actually, let me just show you an example of that. So I coded this up in MATLAB, and so so I have a image here, right? So here's that image that I took in front of a blue screen. And so the way I actually did this was to take it in front of a computer monitor that I had set to showing pure blue. And so just zoom in on this guy here. I guess I can't zoom in too much. So this is not like a perfect blue screen. Like, for example, here you can see that there are going to be some artifacts because on this guy's tail, right, even though I know that this is actually opaque right here, there's reflections that are coming from the monitor onto the front of the object or over the side of the object, right? So in theory, this is kind of violating the matting assumption, right? Because I know that the toy is not transparent there or translucent, it's opaque. This is kind of like a light spill that comes over the edge of the object. And so this kind of blue spill, as they call it, is definitely an issue when you're doing real-world blue screen matting, right? So if you have a blue screen and the person is like too close to it, you're definitely going to see stuff that comes over their body. So if you want to put them a little bit further away from the blue screen, you're not going to have this kind of thing. And in this case, the toy was very close to the computer monitor, and so this was kind of a matting mistake on my part. And so, again, I'm not going to go into the details of like how should you set up your blue screen, although in the book I do make a couple references. There are whole books written on kind of like how-to guides for how you should set up your blue screen and green screen to avoid these kinds of problems. All right. All that being said, so this is the input image, and so again, there's definitely going to be some fuzziness. So especially around the right-hand side of the toy, I expect to get some non-binary alpha values. And then he's holding this little tree, and the tree is not as fuzzy as the toy, so my alpha mat was expected to be a little bit narrower there. And so if I look at my MATLAB editor, so here, and let's see if I can make the font a little bit bigger. I should have thought about this before I came. No, oh, that wasn't good. In fact, I just seem to have done something very bad.
You just collapsed it.
I just collapsed it, so how do I open it up again? Here we go. All right, so I'll figure out how to make the font bigger, but not right now. So basically all I'm doing is exactly the implementation of this Vlahos algorithm. The only extra part is what I'm doing is if the alpha that I get after I do this process is negative, I clip it to 0, and if it's over 1, I clip it to 1, okay? And I have the opportunity to tune these two parameters, right? And so what I can do is here, I'm just going to say my alpha is Vlahos. Actually, I should be able to make this. The problem is this is this new interface of MATLAB that I'm not used to where the preferences are. Because I'd like to make all this stuff bigger. But
It should be the resources, I think.
Resources. Yeah, you'd think so. Oh, resources, okay. Help, environment, layout preferences. Here we go. Fonts. Make this bigger, bigger, bigger. Ah, here we go. Better. Maybe even too good. Okay, so what I'm going to do is I'm going to take, you know, this, and I'm going to say that my A1 is 1 and my A2 is 1, let's say. And I did the rookie mistake of not putting a semicolon. So when I do this, let's see where that image came up. So here I get a alpha mat, and so let's kind of zoom in on here. And so you can kind of see that in the fuzzy regions, you know, I do get this kind of grayscale transition that I expect, right? Instead of it being a hard cardboard cutout of the foreground, I'm getting this kind of grayscale transition from values that are all white in the middle to, kind of grayscale over here in the fuzzy region and then black in the background. And I kind of get the expected behavior that, over here on the little tree that's not as fuzzy, the alpha channel is not as fuzzy either, right? But I can already see that I have these errors that I expected, right? So here in that tail where there's the blue spill, since that's violating the assumption of the matting equation, the Vlahos algorithm is giving me some grayscale there where I should probably have pure white. But, actually, it doesn't work too badly, right? I mean, as a quick and dirty mat, this works pretty well. And that's why I don't really want to spend too much more time on blue screen matting because, frankly, there are pretty good algorithms. And so what you could do also is, again, you could say, okay, could I do better by changing the A1 and A2? And so, again, in practice, when you've got a visual effects artist, they have a whole bunch of possible matting algorithms built into some piece of software that they're using. And so they may have this algorithm with a couple tunable parameters. They may have some other algorithm that they may want to use. So one other interesting insight that I talked to with somebody was that it's also, in practice, very rare that a single matting algorithm is going to give you a beautiful result across the entire image. And in some sense, what you have to end up doing is say, okay, I'm going to apply, the Vlahos algorithm, for example, to this region of the fuzzy image. I'm going to apply some other algorithm to some other region. I'm going to kind of put those together to achieve the final map. In practice, again, as researchers, we're used to thinking that you should just be able to press a button and get the answer and go on with your day. But in practice, it's much more, manual and tweaky and, trying to just get something that works in a certain region of the image. That's the idea. Okay. Another idea that you might think about would be, so that's actually almost all I'm going to say about blue screen and green screen matting. Let me just say one other thing that's kind of related to this is that, well, here I'm still not really head-on addressing the fact that there is this kind of ambiguity in the matting equation, right? So even if I knew the background was pure blue, right? So that's like saying, okay, even if I knew that B was 0, 0, 255, really there's still 3 equations in 4 unknowns, right? The 4 unknowns are the alpha channel and the foreground, right? So the Vlahos algorithm is one way of specifying a thing that will work for the matting equation, but it's not the only way, even if you knew the blue screen. And so there are also some other algorithms that say, okay, suppose that you had some more constraints on the foreground and the background, could you get a mat? One thing you might think about is, okay, so you could also do something that's called difference matting. So difference matting is kind of like saying, okay, let's go back to my MATLAB window here. So here, the idea is I could take a picture of the object I could take a picture of the scene with the object, and I could take a picture of the scene without the object. And I could say, okay, well, places where the, pixels from these 2 images are basically the same should be background. Pixels where there's a big difference between the foreground and the background should be good candidates for where alpha should be close to 1. And so why don't I just basically take the difference between these things and threshold, or use the value of the threshold to get an alpha map. And so I believe I have a algorithm that does that too. So this is what I would call kind of like background subtraction. So what I'm doing here is I'm saying, okay, I'm choosing a threshold. That's what this TH is. And I'm looking at the difference between the foreground and the background. That's what this D3 is. And then D is basically saying, okay, I'm going to look at the sum of squares, or I'm basically looking at the length of this vector, D3. Right? All I'm doing is I'm taking the Euclidean distance to that vector. And then I'm taking places where that distance is above a threshold, and I'm calling those pixels 1. Now, even this is just going to generate for me a hard segmentation, right? Not a continuous alpha map. But the question is, does this get me started, right? And so let's see how this works. What did I call this? BG thresh. So this is kind of like the thresholding I get with one, kind of conservative threshold. And so you could say, okay, well, if I turn the threshold down, I get more stuff that's inside the mat, but I also get more crud from the background, right? And if I turn the threshold up, that means I'm making a more conservative mat, but then I get stuff that I'm starting to lose the middle of the image, right? And part of the reason is that if you look back at the original images, there are parts of the foreground that have very similar colors to the background, right? That's like kind of the same idea where if you have a weatherman who's wearing a blue tie and he goes in front of a blue screen, you may see that his tie disappears, right? So it's the same kind of idea here. So you can't necessarily just assume that everything in the foreground is going to be so different than the background. That's actually kind of one of the reasons why they started doing blue screen and green screen matting in the first place, is that the colors of kind of human skin tones and natural colors that humans wear for clothes are generally not like this bright blue, bright green. And so, they've chosen those colors to be kind of as far away from the human skin tone as possible. You don't see like red screen matting because red is too close to the stuff that you see in people's color tone. Right? Okay, so any questions so far? So let me just ask, or raise the question, so if there's all this ambiguity, how could I possibly actually get the true mat for any image, right? Like, how would I even obtain that, okay? And so one of the answers is, well, if I had different backgrounds, maybe I would have enough information, right? And so let's go back to my screen here. So let's say getting ground truth mats. So, let's go back to our matting equation. I have this image, alpha times foreground, plus 1 minus alpha times background. Okay? Now, let's suppose that I know the background. Okay? So let's say B is known. Right, then I have 3 equations, 4 unknowns. So that's getting closer to what we would need to be able to solve this equation unambiguously, right? And so kind of a natural idea is, okay, well, what if I just kept the object in place and I changed the background, right? So let's say I take 2 images with different known backgrounds. So it's like saying my first image is alpha times the foreground plus 1 minus alpha times background 1, and my second image is alpha times the foreground plus 1 minus alpha times background 2. Okay? So now life is better, right? So now I have basically 6 equations, and I have the same 4 unknowns I had before. Right? So now I have enough information to be able to find that map. Okay? This is under the assumption that when I change the background, the alpha channel doesn't change. And that's something that I think we can roughly safely assume, because the alpha channel is like a property of the foreground. It's like how fuzzy is the foreground, right? So if I change the background, it shouldn't change what the alpha channel is, right? And so basically the 4 unknowns here are alpha, foreground red, foreground green, foreground blue, okay? And so it's kind of just a linear algebra exercise to figure out, okay, well, given this information, how do I get an equation for F and for alpha given these 2 images, okay? And you can find these equations in the book, but basically they come from a really old and important paper called, about triangulation. They called this algorithm triangulation. And so, for example, I showed you the alpha matting website. So that's the way that they obtain their ground truth mats. It's not like they have a grad student who is going through pixel by pixel and labeling alpha values. They take, very high resolution, very high quality images. And I attempted to do the same thing myself. So here, going back to MATLAB, so if I say, let's go back to my blue guy. Oops. And I believe I have a green guy. Oops. Bring my figure up here. So basically, here is the toy on one background, and here's the toy on the other background. And so again, what I did here was, again, the toy is on a tripod, it's in front of my computer monitor, and what I'm doing is I'm attempting to not shake anything, so I have the camera on a self-timer, so I'm not trying to take the picture manually. And all I'm doing is I'm letting the computer cycle through blue and green and trying to get 2 pictures, right? So you can see the registration here is pretty good. The toy doesn't seem to be moving, and that's really important, because if anything in the foreground moves or changes, then my assumption that the 2 images have exactly the same foreground is broken. And so you have to be super careful to make sure that everything is aligned. And so then, if I look at my MATLAB code, I wrote some code that is basically just an implementation of this triangulation algorithm. What it takes in is the image in front of blue, the image in front of green, the known blue color, which is 0, 0, all blue, and the known green color, which is 0, green, 0. And then the equations are really simple to estimate the alpha channel. All it is basically a simple dot product. And so if I do my ground truth thing here, it takes a minute because I wrote this with kind of crummy MATLAB code. So what I'm going to see is, again, an alpha channel. It's not going to look that much different than what you got before. While I'm doing this, let me just say that the only way that you can really make this work in the real world is with static objects like toys, where you can afford to really get your environment the right way to take these really nice background images. Because the other thing is that you also have to acquire the known background image. And it's not necessarily true that you can always assume that the known background image is like pure blue, right? So even if you've got a real blue screen isn't like this fantastic all blue object, right? I mean, it's got, again, if you're lighting it in a sound stage, it's going to have places where the blue is brighter than other blues, and that difference in blues has to be taken into account when you supply the known background, right? So you have to basically get 4 extremely well aligned, very accurate images. The blue background, the green background, the image with the blue, and the image with the green. And so, you can take the time to do this in kind of a lab setting, but in a real-world setting, it's not so easy. And so again, this is the result that you get. It doesn't really look that much different than the Bluescreen matting that I got before. In fact, you can see that there are some weird things here. Like, for example, here at the top of this guy's head, again, there's this kind of, I expect that there shouldn't be this kind of see-through part to this part of the toy. And that, again, comes from the fact that this blue spill and green spill on the object is not satisfying the matting equation, and it's probably satisfying it incorrectly in different ways, depending on whether I'm in the blue image or the green image. And so, this could be done a lot better by me if I wanted to make this really, really accurate, right? And so this is partially because I was doing this at home in front of my computer monitor instead of doing it in a really nicely controlled, nice lighting studio. But all that being said, this is basically the way that you would do it. If you wanted to get the mat 100% for, say that you were doing something like a prop or a what's the word? Like a stand-in or something like that, where you wanted to have some cool thing that you wanted to insert into a clean plate, and you didn't have to worry about it moving or breathing or anything like that. You could take a lot of time to really get a nice mat out of it instead of throwing your visual effects artists at trying to do the outline, right? The other thing, again, is that this thing isn't moving, right? Even if it was so even if you had like a moving toy, right, that would still be pretty hard to do, because the moving toy is at that point no different than a moving human, unless you can exactly repeat the motion over time for these 2 images. So, okay. All right, so that's about all I want to say about blue screen and green screen, right? That kind of gives you an overview of how that kind of thing works. Questions or comments on that? So what I want to talk about next is what happens when we don't have a blue screen or a green screen, right? So what happens when we have just a natural, normal background? And again, that is the kind of thing that researchers are interested in solving because that's a kind of an interesting, hard problem, okay? And so this is where we get into, some more math, okay? So let's talk about natural image matting. So what I'm going to kind of do here is first present you with one of the oldest proposed algorithms for this problem that really people don't use that much anymore. So you shouldn't get the impression that what I'm going to talk about right now is like the way it works in the real world, but it lays the kind of foundation. We're going to use some of the same ideas in some of the algorithms that we're going to talk about on Thursday and on Monday that are really much more like the state of the art in this area, okay? So let's refresh our memories about here is my matting equation. Okay. So the first algorithm I want to talk about is called Bayesian matting. And so this is kind of very early idea. These days Bayesian methods are used all the time in computer vision, and so this was kind of like the first instance of saying, oh, okay, let's apply a Bayesian approach to matting. So here's the idea: is that again, what do I know? I know the image, and I don't know the alpha channel, the foreground, or the background. Okay? And so the Bayesian matting approach is to say, okay, what I would like to do is I would like to maximize this function, the probability of the foreground, the background, and alpha given the image. Okay? So basically what I want to do is these are my unknowns, and this is what I'd like to solve, right? So this is a probabilistic formulation. It's like saying, okay, I want to have a model for given a alpha channel, a foreground, and a background. How likely is that to happen given what I saw in the image? Okay? And so what we're going to do is we're going to use Bayesian reasoning to take this apart into some pieces that we know how to analyze. Okay? So what I want to do is I want to maximize. I'm just rewriting the same equation at the top of the page here. So Bayes' rule tells us that this is the same thing as maximizing the probabilities if I turn it around. Right? So let me just make a little note. So Bayes' rule. So Bayes' rule, hopefully you learned in a probability class long ago. This is basically like saying that if I have the probability of y given x, that's equal to the probability of x given y times the probability of y over the probability of x. Right? So here, the role of the left-hand side is being played by the image, and the role of the right-hand side is being played by the stuff I don't know. Okay? So, how can I try and undo this a little bit? Okay? So, I don't really care about the denominator, and that's typical of these kinds of problems. So what I'm going to say is this is equal to, I guess what I should be, if I'm really proper, I should put like maybe an approximate here. And so the idea here is that there are two terms, right? One is saying if I told you what the foreground, background, and alpha were, what would be the probability of observing the given color in the image? And the other one is a term that says basically on their own merits, what's the probability of having that foreground, background, and alpha term? Okay, and so, if I was being a little bit more mathematical, I would say that there's a part that only depends on the data, right? This part is the only part that depends on the actual image pixels that I see. And that kind of tells me how well do things fit together with my assumption about how the image should be formed. And then there's a prior term. The second term basically says, well, how likely do I think this foreground and background alpha were in the first place, right? And so I can take this apart a little bit more. So typically what you do is you take the log of these guys. You say that, if I'm being really proper, what I should do is I should go back and say that the foreground, background, and alpha, really what I'm doing is I'm finding the F, G, and alpha that maximize these things. And so even though the maxima themselves are changing, the F, B, and alpha that maximize those values are not changing. And so what I'm doing is I'm going to take the log, that's going to turn this product into a sum. And I'm going to make some more assumptions. I'm going to say that, I'm going to assume that the probability of these three guys happening together is nothing more than the individual probabilities multiplied together, right? This is kind of like saying that, the foreground, the background, and the alpha are independent. And again, that's a pretty reasonable assumption to make, right? So if I, have a person in front of a background, there's no statistical connection between the person and the background, right? They're not coupled at all. And the same way, the background and the alpha are definitely not coupled. The assumption that the foreground and the alpha are not coupled is, again, I think that we can make that assumption, but it gets a little bit dicier in terms of, you might argue that there are some foreground colors that are more tightly coupled to fractional alpha values. But let's just make this assumption in the first place. So that means that my matting equation now, what I get is I have the log of this thing. And then the fact that I've got these guys multiplied together means that I can just kind of decouple these guys in this equation. So again, basically, this guy here is what we call the data term. And then these guys here are what we call the prior probabilities, the prior terms. Okay. So now how are we going to actually come up with mathematical formula for what each of these terms should be? Okay. Well, we haven't really yet used the matting equation, right? The matting equation basically says that that's what we're going to use to take apart the data term. So the data term what we need is something that says what's the probability of observing this image intensity given these guys. And the idea is that this should be consistent with the matting equation, right? So basically what I'm going to do is I'm going to make a little assumption like this. So what does this mean? Oops, let me move this over so you can see it. So this means that, I expect that when the matting equation is roughly satisfied by the F, B, A, and I all together, then this term should be high, right? So I expect that when life is good, I want this term inside the norm to be pretty close to 0, right? And then I have e to the 0 power, which is 1, right? So that means that I have high probability when the matting equation is satisfied. When this guy is far from true, right? So if I have an F, B, and A that are really inconsistent with the observed image color, then the term in the norm is really big, and I have e to the some minus big number, which is going to be close to 0, right? So kind of the way I think about this is that, you know, this is my, you know, e to the minus x squared kind of picture, right? Kind of like Gaussian distribution. And so when this number is small, I should be high. When this number is big, I should be low, right? And so all this is saying is that, you know, I, F, B, A should be consistent with the matting equation. And the sigma here inside the, you know, exponent is just something that helps me kind of tune how strict I am about this requirement, right? So if I make sigma, you know, let's see if I can think about this, do this the right way. So if I make sigma small, I don't know why I have the sigma. Yeah, that's okay. So if I make sigma small, that means the Gaussian is smaller. If I make sigma big, that means the Gaussian is wider, right? And so basically, you know, if I want to be really strict about, hey, you got to satisfy the matting equation, then I should have my sigma be small. And if I don't really care so much, or if I want to be a little bit more lenient, maybe because I know that there are some, you know, inconsistencies or some deviations from the real-world matting assumption, then I may allow a little bit of a larger sigma. Okay. So basically, sigma is a tunable parameter. You know, kind of telling us how strict we are. Okay. Now, where do I get the other terms, right? So now I also need to figure out these prior terms, right? So prior terms. I need probability of foreground, probability of background, probability of alpha, right? And again, these are probabilities that come kind of from the outside, right? It's like me saying as an observer, okay, well, what do I think the foreground distribution is? What do I think the background distribution is? What do I think the alpha distribution is? Okay. Now, for example, let's think about Bluescreen matting again. So in Bluescreen matting, I have a very strong prior that the B numbers are very close to pure blue, right? In natural image matting, I may not necessarily have that same kind of strong intuition. And so what I could do is obtain those, and that's exactly where this Trymap comes in. So let's go back. So let's see, basically these guys come from Trimap, or they come from Scribbles. Right, so let's go back to my PDF here. Whoops, I don't know why that didn't go. Right, so if I have a Trimap, basically this is me as the user giving the algorithm a whole bunch of prior information. It's like saying, okay, all these pixels inside the middle of the image, the white pixels, I know are foreground. All the pixels outside I know are background, right? Those help me build my distributions, my PDFs for foreground and background. I could do the same thing if I had Scribbles. I would have a little bit less to work with, but I'd still have a whole bunch of labeled pixels that are either foreground or background. I can use those to build models. And so this, I guess, is this guy. Okay, sorry. So here's kind of an example of how the Trimap would help with that, right? So here, I've got the Trimap on the left, and I've got the distributions that come from that Trimap on the right. And so here, these black dots are the colors that have come from the black region of the Trimap. And you can kind of see that since this was a blue screen image, that all those guys are really clustered really well around the blue part of the screen, right? So basically, what I have is red is close to 0, green is close to 0, blue is very high. And then the stuff in the middle of the image, the stuff that the user has labeled as definitely foreground, is a much wider distribution, right? So in this case, you know, there's not a lot of blue. I mean, it's hard to tell because this is a 3D projection of or this is a 2D projection of a 3D image. I really have to show you this and let you kind of rotate it around to see the distribution of the points. But here you can see that the foreground intensities are really well separated from the background intensities, okay? And so what I could do, for example, is if I look at this, I say, okay, well, I could fit these kind of ellipsoids to this data, right? The first thing that you would naturally do as a computer vision person is try and fit Gaussians to stuff, right? So the idea is that what I could do is I could say, okay, I'm going to fit Gaussian PDFs to colors labeled in the Trimap. Right? So just as a reminder, this Gaussian PDF might look like, you know, the PDF for B could be, to make it something like this. So what is the Gaussian PDF? It's this messy equation. All we're saying here basically is that what I have is I have a mean, right, which is the middle of the distribution, and I have a sigma, which basically tells me the shape of the ellipse around that mean, and I can plug this in for the probability of F and the probability of B, right? Now, this guy, the probability for alpha, right, that's a little bit trickier because I don't know anything about what I expect the alpha channel distribution to be. And so one assumption that you could make, and that the original Bayesian matting paper made, was that this was constant, right? Basically saying that any value of alpha was equally likely to any other value of alpha. I'm just going to say that's a highly questionable assumption. We're going to come back to that in just a second. But that's the assumption that they made for this case. And so if you put this all together, you can basically make a closed form solution. So let me just write over here that basically the Gaussian assumptions for these guys and the constant assumption for the alpha lead to a nice closed form solution for F, B, and alpha. What I mean by that is that if I went back to my original formulation, this guy here, right, if I took this thing and then I plugged in the forms of the functions that I just told you on the last couple of slides, how would I, solve that equation? What I'd do is I would take the derivative and I would set it equal to 0, and I would find the F, B, and alpha that solved that equation. That's exactly what these guys did in the Bayesian matting problem. And so that's nice. Basically what it looks like is, I have some messy 6x6 equation. So basically what I get is a linear system that says, okay, I know all the stuff here, I know all the stuff here, I can solve this system for F and B, and then my alpha is basically a very simple closed form solution. So you can refer to the book for the details of exactly how I populate these matrices and vectors, but basically it's not so hard to do. And so if I toggle over to the website for this paper, which again is like ancient, I mean this is actually 2001, right? So this is like already a 12-year-old paper. But at the time there wasn't a lot of work on this, and so you can see pictures along these lines of what they were doing. They were taking pictures of wispy objects, so they actually, some of it is stock photography. Even this was kind of before the days of stock photography being so available, and so I know that a lot of these researchers actually went out to, they hired actors in frizzy wigs to stand in front of natural environments and collected data and then use that to seed things in the community. So you can read the original paper if you want, but this is kind of the idea, is that they compared different things. They compared Bluescreen matting, which we talked about, difference matting, which is like Bluescreen matting, but you have a just general background with the object in front of it and the object without it, or the background with the object and the background without the object. And then they compared their results to natural image matting. And so they showed that their results look pretty good. And so here they're kind of doing some comparisons between previously proposed matting algorithms and theirs, right? And so like this Mishima algorithm, for example, you can see did a pretty crappy job pulling the mat on this dog because there's all this blue screen stuff that is still on the edges of the image. Whereas their Bayesian matting algorithm on the dog looks pretty good. And again, they have ground truth. The ground truth comes from this triangulation method I talked about earlier, where they very carefully acquire the foreground object in front of two different backgrounds. And so here, again, they're just comparing a bunch of algorithms that were kind of on the shelf at the time and showing details of why their algorithm is better. So their algorithm is this one where my cursor is. You can see this previous algorithm, for example, produced mats that were a lot kind of grainier and blockier compared to a mat like this. And so again, here's a kind of an example where here this mat is like way too blurry, and if you were to look at it, you could see that it doesn't do a very good job. So as with every computer vision algorithm, whenever you propose something new, you have to verify it or validate it against the state of the art. And that's what these guys were doing at the time. Now, these days, Bayesian matting is not the state of the art anymore, and stuff kind of blows that out of the water by a lot, but this was the first kind of such approach. So let me just say a couple more things about these PDFs. So one is that, where'd my PDF go? Oh, here we go. One is that, this Bluescreen case, life is good because the distributions are very well separated in color space, right? So it's easy to draw kind of a nice ellipse around the colors in the foreground and a nice ellipse in the colors in the background, and there's not a lot of contamination. Here is a case that's much more complicated. This comes from a case where the background is natural, right? So here you can see that the black dots are the background samples and the white dots are the foreground samples. And on the left-hand image, you can see that there's a lot of overlap between those two populations of colors. And so if I tried to draw an ellipse that kind of encompassed the foreground and another one that encompassed the background, those two things would overlap. And that would be bad for the algorithm because it would not be able to tell whether a given color was really much more likely to be foreground or background. And so one thing that you can do there is the right-hand image, where instead of using a single Gaussian, a single ellipse to represent the color distribution, you could do what's called a Gaussian mixture model, where you say, okay, I'm going to make my distribution out of a bunch of separate little Gaussians that kind of add up to be the full distribution. So here I drew two Gaussians around little background populations and three Gaussians around little foreground populations, and that way I can kind of really more clearly separate what's foreground and what's background. The bad news is that in this case, it's no longer possible to do some really nice closed form algorithm to obtain the alpha, right? I talk about in the book a little bit about, it's not like the end of the world, but you do have to do a little bit more work to get there. Another thing is that, you would think that it would make more sense to collect this foreground and background distribution, not just like looking at the entire image, the entire Trimap, but what I should be doing, you could say, is, okay, so if I want to figure out what the mat should be over in this region of the image, well, I shouldn't be using foreground and background distributions from the entire image. I should just be using foreground and background, like foreground from over here and background from over here, not from like way over here where the colors are different and don't really matter, right? And so that kind of idea of deciding which samples of the Trimap to use for the foreground and the background is going to come back at us in a couple lectures. But here's the idea, is that what I would do is I would say, okay, here's the pixel I need to make a decision about. What I do is I take the foreground samples that are nearby and the background samples that are nearby, and I use those to build kind of local distributions for foreground and background, right? That makes a lot more sense because it's customized to what exactly is happening right at that pixel, right? And so lots of future matting methods we're going to talk about, they differ slightly in how they do the sampling. Most of them do something along this line, where you're basically looking at just local samples to get foreground and background. The last thing I want to talk about is that, we made the assumption here that the alpha channel was, the probability of getting alpha equals 1 or alpha equals 0.3 or alpha equals 0.7 are all basically the same. And that doesn't really make a lot of sense. So if you look at actual statistics from real data, so first of all, I should know, right, that most alpha values are either very close to 0 or very close to 1, right? Certainly if I look at the Trimap and I look at the alpha values, well, if I look at the ground truth alpha map for something, right, that's what this left-hand picture is. So basically I get lots of background, lots of foreground, and then basically not too much stuff in between. If I only look at the trimap, though, so here this is like saying over the gray region of the image, the pixels that I think are fractional alpha values, even here, there's more stuff that is close to 0 and more stuff that is close to 1 than stuff that's right in the middle. And so instead of assuming that I have like a constant line across here, what you could do is you could fit a different kind of distribution to this, P of alpha, right? And for example, this is what's called a beta distribution. So a beta distribution is low in the middle and high at both ends. And this is a much better fit for what actually occurs when you look at real alpha values. But again, the downside is when I do this, that I'm not able to get this nice closed form solution. I have to do something that's numerical. And again, as computer vision researchers, we shouldn't necessarily shy away from doing numerical stuff, right? That's really what we do in our real world, in our real world stuff. Even though we like to get closed form solutions, you may not always be able to. So the question is, could you do better with this better model? Okay, so the last thing I want to say is that nothing I've talked about so far is explicitly taking account of the fact that we expect that the alpha values for nearby pixels in the image to be similar, right? We want there to be some sort of a some sort of a spatial coherence between the foreground, the background, and the alpha, right? We don't want those to look like just static noise images, right? And so next we're going to talk about algorithms that really start to take this spatial coherence into effect, or into account, saying less, my decision about the foreground background alpha at this pixel should be related or should be consistent with the foreground background alpha at my neighbor, right? Those will end up producing much better mats, right? Because we know that conforms with physical reality. And so we're going to start talking about some more algorithms like that next time. Okay, so with that, I will pause and ask any questions. Okay, so for those of you who came in a little bit later, the first homework is on Piazza. If you're not on Piazza, then you should email me to make sure that you see what the homework is. Let's see, I have my office hours on Thursday. I think I need to do something at 3 o'clock this Thursday, though. So I am going to probably start my office hours at 4. Please watch Piazza for details on that. And hopefully I can stop the recording, and I'll put the recording up as soon as I figure out how. And as soon as I can figure out how to get to my recording tab.